All right, good evening everyone. So it's a pleasure to be here and to give you an overview of what IMEC is doing in the field of semiconductor technology, and also discuss how we help to bring innovations to a global ecosystem of players in semiconductor technology. So I think we heard today many people talking about all the opportunities that we have in the ICT industry, and actually a lot of the semiconductor development has been driven by the needs for data centers, smart mobile devices, and the next wave coming up is also smart sensors, where we will be interconnecting things and people and talking about trillions of devices being installed worldwide. Now, to develop the technology that is necessary to have all this, we need to take into account a number of things, and an important part of it is that whatever we do, everything is constrained with respect to energy. Data centers, smart mobile devices, which are battery constraints, and definitely if you move into the smart sensor area as well, everything needs to operate at ultra-low powers. So, technology trends that we see is obviously device scaling. Yeah? We are continuously scaling transistors to smaller dimensions, and IMEC's mission is to do the technology pathfinding 2 nodes ahead of what industry is using today. And that means that our focus today is 14, 10 nanometers, and we are also exploring beyond 10 nanometer options today. In parallel, there is also 3D technology that will allow us to actually perform system scaling, and that allows us also to integrate other technologies today that will be important to improve system performance, such as optical technologies. Now, device scaling traditionally has always been enabled by lithography, and lithography, of course, will continue to do so, but there is more than lithography only needed to do that. And today, scaling a transistor involves the very complex technology of lithography together with new materials and new device concepts. The 3D technology will need to go hand in hand with all of these and make sure that we can integrate the leading edge technologies together with other types of technologies that you need to perform specific functions which not necessarily need scaling. So going from one node to another, we still need to make sure that we can increase our performance, have our power reduction, area reduction, and at the end, cost reduction. So if you take a look at lithography today, we have quite a big effort on EUV lithography and making sure it is available to the industry. As you can see from the graph depicted below, double patterning will run out of steam below the 30 or 40 nanometer resolution half pitch. And if you want to avoid going to triple patterning or quadruple patterning, definitely EUV will be needed there. At IMEC, we've always had access to one of the first tools available on EUV lithography. Today we have a 3100 system installed, and a 3300 will come soon to IMEC, which will allow us to further make progress on this technology. I think great progress already has been made in terms of the overlay matching that we can achieve, and also if you take a look how far we have pushed resist technology to enable features down to 60 nanometer half pitch. But still all of challenges remain, especially with the throughput of the system and the source associated to that needs to deliver higher power to the wafer. So if you take a look at the logic device roadmap, actually these give you an overview of all the innovations that are needed to continue scaling a transistor. So we started with introducing strain and advanced gate stacks for the 45 and 32 nanometer nodes, and now are moving into fully depleted channels that can be either thin film body SOI or it's 3D Finfets. If you want to scale further, going down to the 10 nanometer node, even that will not be sufficient anymore, and we really need to do radical material changes. And this is where we are investigating 3-5 materials, high mobility channels, in order to make sure that we can lower the supply voltage. Yeah? And if you look further down below, going to 7 nanometers and beyond, it will require different device architectures. You need to go to 3D devices, vertical devices, in order to make sure that you still save on the area. And 5 nanometers and below, probably a complete new material system, and we're investigating carbon-based materials there. So let's go a little bit in depth in some of the aspects that we're doing on device scaling. So Finfet is, of course, an innovation. We started with that already in 2003, and it's today already in production with the leading edge, and foundries are going to put that in production as well soon. And IMEC is actually pioneering, together with the leading edge companies, what are all the technology options to make a Finfet work at the 14 and 10 nanometer node. Definitely that involves a lot of engineering work in terms of special implants, but also advanced gate stack. All the high K and metal gates that were developed for planar technologies need to be integrated on a 3D structure, which is not a straightforward task. Further going down to 10 nanometer, we are now exploring how to change the silicon channel altogether and replace that with 3.5 based materials. And you need to do that on one wafer in a CMOS-like style. So today we are pioneering with leading edge equipment that we get from our equipment suppliers, how to grow those 3.5 materials on 300 millimeter wafers, study the growth mechanisms, make sure that you keep your defects under control, and in the end achieve the device specs that are necessary for a 10 nanometer node. If you go further down, looking at the 7 nanometer node, in order to still do the area scaling, we're looking at complete vertical devices and tunnel FETs. Yeah? And those devices hold the promise that we can actually switch those below the 60 millivolt per decade and make sure that we can keep leakage under control. So we are doing very early explorations of these device concepts at IMEC and sharing these data in a very early stage with our research partners. Further down the 7 nanometer node, we're looking at completely different material systems, and graphene is one of the candidates that we're looking at, and a lot of R&D work is ongoing in understanding how we can reliably grow those materials, influence the properties, and how to make actually devices in those materials that can be of use to the industry. Not only on logic scaling, there are a lot of new opportunities. Also in terms of memory, new opportunities are arising. And what we see appearing is that there is an increased interest to have access to integrated non-volatile technology. And some of the materials and candidates that we are looking at is resistive RAM for data storage, and also STT-RRAM that can play a role both for DRAM as well as for SRAM applications. So there is quite a lot of interest from the companies that are partnering with us in exploring those technology options for the very advanced nodes. So you see some of the results that we're doing for resistive RAM. There is quite a plethora of material systems that is out there, and IMEC is studying quite a number of them. And what we are providing to our industry partners is very early feedback on which material system is the most promising ones, which are the least promising ones. And that avoids, of course, very costly investments of our partners in the program, and they can, bet on the right horse straight away. So this is one of the examples where we demonstrated an RM cell in a 10 nanometer crossbar dimensions, which are really the dimensions where these technologies are going to be used. And we get promising characteristics on the switching behavior and on the endurance of that material system. If you look at system scaling technologies, then of course TSV technology will play a very central role. And we envisage that in the future, we will have cubes, stacks of chips that will communicate to each other, either directly by stacking them on top of each other or side by side through interposer technology. And obviously, you need very high performance, high bandwidth communication links between those cubes. And there we are looking at optical technology to be the next interconnect technology to provide that high bandwidth communication. Stacking technology today is reaching a maturity stage, and it is going to enter into production soon for several types of applications. And we are pioneering how to make TSVs, studying the stacking aspects, and also studying how you can further scale the dimension of the TSV interconnect. And what is, of course, very challenging is that you need to make interconnects in chips of the size of, let's say, a couple of micron of copper that you stick next to a whole bunch of Finfets, which have nanometer dimensions. And that puts quite a challenge to the technology development. One of the challenges that you need to deal with is that these big piles of copper actually create a lot of stress in the silicon. And because of that, it affects actually the operation of your transistors nearby. So we model actually the stress that is being created in the silicon. We have special test chips where we can validate finite element models together with real experimental data. And that helps us to further improve the models and integrate them in the EDA workflow and make those available to our partners. And that helps them to define the right set of design rules, how they can actually safely integrate TSV interconnects in their advanced systems.